Hello everybody. In this video we are going to show you some of the problems from equilibrium of a rigid body. Okay, before I go there to that problem solving part, I'd like to summarize of the theory what you already learned from the other videos. Okay, now first of all, what is a rigid body? A rigid body is something that which will not deform its shape because of the applied load or moments. Okay, let's say this is a steel beam here and this part is fixed. So if you try to pull that one with a certain force, so this one will not elongate. Similarly, if you apply some compressive load, compression, then basically you will also see that this member is not shrinking. Okay. Similarly, if you apply a moment here, then basically this one will not be subjected to any bending. Now, definitely the amount of load, this is very, very important. If you apply like 10 pounds here, maybe this one will not, like compress, but if you apply 10 tons of load, then basically this one might shrink. So that depends on the size of this member or what type of member we are talking about, right? That's actually you are gonna learn in your next, class, which is called the mechanics of solids or strength of materials class. Okay, we are not gonna go there, but we are assuming that a rigid member is something that is not gonna change or deform its shape because of the applied external load. Okay, so let's say for for a cable here hanging from this beam. Now you can see if you apply load this way, this one will not deform, but if you apply any moment here, then basically this one will deform, right? So that's why the cable or chain, these are not like rigid members. Okay, now what is in equilibrium? What does it mean? It means, like the summation, you already learned that one in chapter 3, that the summation of forces in every direction is basically 0. Okay, so you can see that one also from Newton's second law, that force is equal to ma, since a equal to 0 for any stable member, so the summation of force, that has to be also 0 here. But that's only for concurrent forces, which means like if you equilibrium of a particle, like if you have force here and you have force here, and if you have force here, and if the summation of forces in x direction and y direction is 0, then basically you can see that the particle is in equilibrium. But the rigid body is a little bit different because the force will not be concurrent. So as I showed that one here, so let's say I have one force here and another force is here. Then basically you can see the forces are not, like concurrent here. They are just working at different location of the rigid body. Now, even for example, if I assume that the summation of forces in, let's say, y direction is also 0, because I'm gonna put another 10 pounds load here. Now you can see summation of fy is equal to 0, summation of fx equal to 0. But this one can rotate like this, right? So there is a moment here. So basically, if you can't, resist that moment, then this will not be in equilibrium, right? So for condition of equilibrium, we need like one more equation here to satisfy the equilibrium for a rigid member, which is actually summation of moment at any point here. Okay, it could be here or here or here. Summation of moment is also 0. So you can see we have now 3 equations, so we can handle 3 different 3 unknowns from there, right? Now, in most of the cases, you can see I have force here, but and you can see that I have a moment here, but it's not rotating. Why? Because there is a support. So support is providing the reaction. Now, the type of support that also tell you like what kind of reaction you are expecting from there. Okay, let's say for example, it's a very common, like structural support. We call that one like pin support or hinge support, and this one is a roller. Okay, now I have some loads here. The reaction here, that depends on the external load. These are called the external load. Okay, let's say based on that external load, I'll get some reaction here. Like for myself, let's say my weight is 200 pounds. Okay, so what would be the reaction in the floor? Definitely it's 200 pounds, right? If I hold a book here and my weight is 210, then basically the reaction will change to 210 because it's always equal and opposite, right? Now you can see here, like let's say this is a steel member here, and the steel member will change its length because of the temperature variation. In summertime, you can understand the temperature will be very high. That time, this one will try to elongate this way. Okay, that's why we usually put a roller here, so that if the length increases, then basically this one can increase a little bit there too, because the roller can roll. Okay, so there is a reason. That's why like we are using this one. Here is like a hinge. Hinge is something like this. Okay, if you pull that one, you cannot. It will resist. So it will offer a reaction. If you try to, like put like the other direction here, force, you cannot do that because it's offering resistance. But if you try to rotate that one along that direction, then you can see there is a pin here, and this one can allow that to rotate. Means like this one will try to rotate, and this means like this support doesn't offer any resistance for rotation. Okay, so that would be 0 actually, 0 resistance for rotation. So the reaction would be only the horizontal force and vertical force here, right? So you have to take a look here, table number 5.1, and they will show you different type of support system and what type of reaction you are gonna expect from there. Okay, but I'm gonna show you some of the very common, support system that we usually see in many cases here. Okay, so as we said, this is your hinge support or pin support. Looks like this. You see there is a pin here, so this means like this one can rotate like this, but if you take this reaction out, then basically you can show that one with two different forces here. Okay, Fy and Fx. Similarly, if it is a roller, then basically this one, if you apply load to the horizontal direction, it can't protect. It doesn't offer any reaction here, and this one will start moving. Okay. Similarly, if you try to rotate that one, this one will rotate. But if you apply load here, then basically you will see that this one will try to protect that one and offer a resistance. So we can just show one force here. Okay. Similarly, if this is a fixed support, let's say this is fixed with a wall here, and you apply load here or moment here, then you can see this one is taking all the moment as well as the force in that direction. So actually we can replace this reaction with this. Fy, Fx, and also a moment, counterclockwise moment, so that this one will be equal with this one. Okay, so the total moment here has to be 0 to stand that one. Now, to solve that problem, what we have to do quite often is like draw the free body diagram. What does it mean? It means like you have to take that member out and replace the supports with different type of reaction, and how many reaction you are expecting there, that depends on what type of support is there. So if you take a look the table number 5.1 in your textbook, then basically you will be able to see that what kind of like supports are most common for a structural purpose. Okay, now let's move forward like to problem number 5-16, and then we'll try to show you how to draw the free body diagram for all of the problems what I'm going to solve here. We'll draw the free body diagram first, and then basically we'll use these three equations like summation of Fx, summation of Fy, and summation of moment at any point is equal to 0. From that three equations, we'll try to solve the problems in this chapter. Okay, now let's move forward. In this problem here, you can see this one is saying that this is a beam ABC. There is a weight here, 80 pounds, and you can see this one is hanging from a pulley here. So this is cable, same cable moving over the pulley here. They are asking you to find out the reaction here as well as the tension in the cable. Okay, so the first thing what we do here is draw the free body diagram of this member here ABC. Okay, to do that, you can see this is a pin support, and for a pin support actually we have two reaction here. One is Fy, this is your Fx, this is the point A actually. Now you can see here I have also, I'll try to take this part off from there when I draw the free body diagram here. Now if I cut a cable, then basically you will see tension there, right? But you can see this is the same cable here. So if I cut it here, so you will see, since this is the same rope, so the tension here and tension here is basically same tension, which is T here. Okay, so you can see I have three unknowns here, T, Fx, and Fy. Now what we have to do, we have three equations here, summation of Fx, summation of Fy, and summation of moment. Now you can ask like which equation you were gonna do first. Most of the cases you will see, there is no hard and fast rule there though, but most of the cases you see that taking moment at a particular point would be very, very helpful. And where you want to take the moment, that's also a very, very important question. So you always have to take the moment to avoid maximum number of unknowns. Means like you have to take moment at that point at which the number of unknown is maximum. Okay, for this particular situation you can see you can take your moment here, 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 or here. Now the thing is, like if I take my moment at A, then basically Fy and Fx is passing through the point A, so I can avoid these two unknowns and find out my T from here. Okay, now so here if you take the summation of moment at A, let's say this is clockwise moment, so you can see for this one clockwise is positive, and the summation of moment has to be 0 because this is in equilibrium condition. So you can see this force T multiplied by 5, that's counterclockwise, so negative T into 5. Then you can see this one is actually, you can find out that angle here, so your theta is tan inverse 2 by 1. That's basically 63.43. So if you see, like if you take the component horizontal direction, that would be T cosine 63.43, and this one will pass through point A, so it doesn't have any moment. Okay, so you can see the other component in the vertical direction, which is actually T sine 63.43 multiplied by 10, and I put that negative sign because this one is counterclockwise again, right? Or what I can do, I can just assume this one is counterclockwise, then this one will be positive, right? That's up to you. Let's say here I'm assuming this counterclockwise is positive. So this one would be this plus this, right? Now you can see for these four, this is actually trying to rotate clockwise along A. So this one would be minus 80 multiplied by the distance 13. Okay, so if you solve for that, then basically you will get T is equal to 74.6 pounds. Okay, now once you get this one, then basically you can find out Fx and Fy quite easily, because you can take the summation of force in x direction and summation of force in the y direction. So let's say summation of Fx equal to 0. So this is Fx minus the component of this one, which is T cosine 63.43. That's equal to 0. So your Fx equal to T is 74.6 cosine 63.43, which is basically 33.4 pounds. Similarly, you can take the summation of forces in y direction and find out your Fy here. Okay, so let's say summation of Fy equal to 0, your positive direction. So you can see Fy plus this way plus T. Then you can see this one is here is plus T sine 63.43 minus 80 is equal to 0. Okay, so if you plug the value of T here and find out your Fy, that would be actually 61.3 pounds. Okay, so this is basically your answer here. Now let's move forward. Problem number 5-29. Okay, this one is saying that 50 kg wheel, there is a block here which is 50 millimeter thick here. Find out the force P so that this one will just try to overcome, this obstacle here. Now you can understand that when you are pulling that one, when this one is just tipping at that point or crossing that one, actually this one will come up from that surface, means like there is no reaction at that surface. Okay, everything will work here at the tip of this point here. Okay, so if I try to draw the free body diagram of this one, then basically this one will look like this. So the force is working at this point here, which is point B, and you can see I can also show you the distance of this one. So basically from here to here is 30 millimeter and from here to here is 5 millimeter. So this one is actually from here to here is 25 millimeter. Now if you see this triangle, then this is 30 millimeter because this is the radius. So this distance would be root over 0.3 minus now you have also the weight that's working at the centroid, so we can show that one here. And that is 50 kg. That many Newton here. So you can see I have three forces. This is my reaction, let's say reaction here. And then you can see the 50 kg force here and the pulling force P. Okay, so now if I take the summation of force, or if I take the moment at point B, summation of moment at point B, let's counterclockwise is positive. So you can see this one is actually going through that point B, so this one doesn't have any moment. Okay, now you can see here what we can do, we can just dissolve that force P into one component this way and one component this way, and we can find out what would be the distance of that force from there, right? So you can see if I take the P cosine 30, that's the force in this direction, and you can see the distance, perpendicular distance from point B to that force is equal to from here to here. That's actually 25 millimeter, right? Now you can see you have one force here that's going upward here, which is P sine 30. And the distance of that force, line of action of that force from point B is from here to here, which is 0.166. And then you have that force, like the weight of that wheel, which is working like clockwise with respect to point B, so that would be negative 50 into 9.81, and the distance from here to here is actually 0.166. So that's actually 0.216 P plus 0.083 P, that's actually 81.42. So your P is basically 272.3 Newton. So that's the minimum amount of force you need to pull that wheel on that obstruction here. Okay? Now let's move forward. Problem number 5-36. Okay? This one is saying that the beam of negligible weight is supported horizontally by two springs. If the beam is horizontal and the springs are unstretched when the load is removed, determine the angle of tilt of the beam when the load is applied. Okay, so that's that triangular load here, and this one will try to, because it's like one-sided, so basically this one is gonna move vertically here and maybe a little bit here. Now we have to find out the tilt of this beam here. Okay, now draw the free body diagram first. So I'll just take, let's say, this force up from here, because these are cables. So let's say this is FA, this is FB, and I'll simplify that distributed load here so you can understand that will cause a vertical load, which is actually 2/3 from here, and that would be equal to half into 3 into 600, which is actually 900 Newton per meter actually. Okay, so just for clarity, you can take this one off here. So I have basically 3 forces here, like 2 reaction and the external force here. Now the distance from here to here is actually 2 meters. Okay, now if I take the summation of moment at point C, let's say counterclockwise is positive. So you can see FB multiplied by 6 minus 900 multiplied by 2 is equal to 0. So your FB is equal to 300 Newton. Similarly, you can just take a moment at D and you can find out your FA, right? So summation of moment at D equal to 0. So you can see minus FA multiplied by 6 plus 900 multiplied by 4 is equal to 0. So FA is equal to 600 Newton. Once we know the force working on the spring, we can just find out the deformation in the spring, right? So let's say the deformation here is XA. So F is equal to FA is equal to, let's say this is XA here, is KA into XA. So basically XA equal to FA divided by KA. So this one is FA is 600 Newton, and this is actually KA is 1 kilonewton per meter, or 1000 Newton per meter. So this is actually 0.6 meter. Okay. Similarly, you can find out your XB, which is FB divided by KB. So this is 300 Newton divided by 1500 Newton. Because KB is 1.5 kilonewton, means like 1500 Newton per meter. So which is actually 0.2 meter. So if I try to show that one here, that what is the tilt here, then basically you will see the center line of that point that's moved from here to here, which is 0.2 meter, and this one will move from here to here, which is 0.6 meter. Okay, so the tilt is here. So you can see this one is actually 0.4 meter, and the total length from here to here is actually 6 meter. Now you can find out this angle here. That's what they are actually asking. So since this one is not gonna change its length, so this length and this length is same, like 6 meter here. So you can assume like r theta is 0.4 meter, and r is basically 6 here. So theta is equal to 0.4 by 6 radian, which is actually 0.4 into 180 divided by pi radian. So if you solve that one, then basically you get 3.82 degree. So that's basically the tilt of the beam after applying that load here. So this angle is small enough. So sometimes you can also use like, theta is equal to sine inverse 0.4 by 6. That's also 3.82. Or tan inverse like this divided by this. You are gonna get very similar answer. Okay? Now let's move forward. Problem number 5-44. Okay? So this one is saying that the 10 kg uniform rod is pinned at end A. If it is also subjected to a couple moment of 50 Newton meter, determine the smallest angle theta for equilibrium. The spring is unstretched when theta equal to 0 and has a stiffness of K equal to 60 Newton per meter. Okay, so this is the figure here. So this is the rod, 2 meter rod. This one is trying to rotate this way, and that spring is trying to push it back there. So they are asking like that, what theta this rotation here and this spring is trying to pull that one, they will be in equilibrium. Okay, now let's draw the figure here. First of all, you can see that initially they are saying this one is from here to here, and then this one, when we apply this one, let's say at equilibrium this one moves from here to here. So how much movement occurred here? That's basically this distance here. That's your movement S, which is equal to, you can see this is actually 2 sine theta. Okay, that's your S. Now we know that your force is basically K into S. So you can see K is basically 60 Newton meter. So 60 into 2 sine theta. So actually that's 120 sine theta. So this one here is basically 120 sine theta. That's the force working here. And here is like 50 Newton meter. We have to find out the theta here. And this is the weight of the beam, which is 10 kg. So that would be actually 10 into 9.81. Now if I take a moment at A, this is my point A here. This is a pin, so I just put the two reaction here, AX and AY. And you can see that I have actually three unknowns here, AX, AY, and theta. So if I take the moment at A, then basically I can avoid AX and AY from there, right? Let's take a moment at point A, okay? So if you take the summation of forces, or summation of moment, summation of moment at A, and let's say this is counterclockwise is positive, that has to be 0 here. So you can see that this one is actually causing counterclockwise moment, which is if you take a component of that force into this direction and this direction, then basically this direction is going through point A, so only this direction, which is 120 sine theta, and then cosine theta multiplied by the distance, which is actually 2 meters from here. And this one is negative. And the distance from here to here, actually you can see this one, you can take the component of that force this direction and this direction, right? So the cosine one will actually passing through point A, so I'll just say the sine theta, and then multiply that one with the distance from here, which is 1 meter, okay, and minus this 50 Newton meter is actually 0. So you can see that's 240 sine theta cosine theta minus 98.1 sine theta actually equal to 50. Okay, so that's the equation we get there. Now it's kind of difficult to solve that equation here, so we'll try to do that one like the numerical solution, okay, which means like trial and error method. We'll just assume like any value of theta here and try to see the left side that time would be equal to 50 or not, okay? So you can just get your different theta value, and this is your left hand side. Right hand side is not gonna change. That has to be 50 all the time. I'll just start with 10, 15, 20, 25, and plug that value here and see that what is the magnitude of this thing in the left side. So actually when you get 24.6 degree, then basically you get your left hand side is 50 and and right hand side is 50. This means like at a value of 24.6 degree, this equation actually satisfies. Okay, so that's why the angle would be 24.6 degree. Okay, let's move forward. Problem number 5-49. Okay, this one is saying the rigid metal strip of negligible weight is used as a part of an electromagnetic switch. If the stiffness of the spring at A and B is K equal to 5 Newton per meter, and the strip is originally horizontal when the springs are unstretched, determine the smallest force needed to contact the gap at point C. Okay, so they gave you the stiffness of this one and this one, and you have to find out the smallest force Fc, which will like cause the close of the gap so that the switch can act. Okay, now let's draw the free body diagram first, and then we'll move forward. Okay, so draw the free body diagram. I'll show that one with two forces here. Now, if you take a moment at A, or if you take a moment at B, that's up to you. But you can see here, let's say summation of moment at A equal to 0. Let's say this is clockwise. So Fc multiplied by 100 millimeter minus Fb into 50 millimeter, that's equal to 0. So you can see Fb basically equal to 2 Fc. Similarly, if you take a moment at point B, let's say clockwise is positive, so you can see Fc into 50 minus Fa into 50, that's equal to 0, so Fa is equal to Fc. Okay, or you can say Fb is equal to 2 Fa. Okay, so we can see actually this one is double of this one. Okay, so if this is F, then this is also F, and this one is basically 2F. Okay, since the stiffness is same here and here, but this force is double, this means that the deformation at point B is double than deformation at point C. Okay, so let's say this is 50 millimeter here, this is 10 millimeter here, and this is, let's say this distance from here to here is x, and the total distance from here to here is 50. Okay, now we also know if this is x at A, then this one has to be 2x A, because the force is double here and they have same spring constant. So this distance is basically twice than this distance. Okay. Now, if I consider this two, similar triangle, then I can say XA divided by X is equal to 2XA divided by 50 minus X. Okay, so if you take X cancel here, so you can see like basically twice X is equal to 50 minus X, so basically 3X equal to 50, so X equal to 16.67 millimeter. Okay, so here from here to here is basically 16. Now we can also try to find out, like if I just consider this triangle and this triangle, or this triangle and this triangle, then basically you can see 2XA divided by the distance from here to here, which is basically 33.33. is equal to 10 divided by the distance from here to here, that's actually 83.33. And then you can find out your XA from here. Now we can just go back and try to see actually what force will cause, if that F here is also F, and here the deformation is 2 millimeter. So what force will cause 2 millimeter deformation? F equal to, we know F is equal to K into X, let's say for point A, and our K is 5 Newton per meter. Multiplied by XA, which is 0.002, that's actually 10 millinewton. Millinewton means like 10 to the power minus 3 Newton. Okay, so we need a very small force to close that gap. Okay, thank you for watching.